Good afternoon, good morning, good whatever it is to you. This is Stereo Police. I will be mounting this camera to a tripod, never fear. This is just temporary. Welcome to Lecture 1 at Audiophile University. Lecture 1 will be called, or titled, Charge and Current. And I want to say this is probably going to be my longest and most tedious lecture, but it's absolutely necessary because it's the foundation of everything. Everything. And you always need to establish a good foundation, to build everything on. And this is probably where a lot of the misunderstanding about electronics comes from. And so I promise you, if you bear with me through this and pay attention to everything, you're going to come out of this a whole lot more knowledgeable. And you're going to learn, unless you're already a physicist, but you're going to learn, if you're the average non-technical audiophile, you're going to learn a couple of things that are shocking. Pun intended. I'm going to start with a demonstration, but let me say this first. And again, I will be mounting this camera to a tripod, okay? So sorry if you're getting seasick. Electric current is not defined as the flow of electrons through a conductor. All right? It's not. After understanding this lecture, when you hear people say this, just smile to yourself. Just smile. Okay, in a circuit, electrons do migrate in a direction generally from negative to positive charge. But a baby can crawl faster than an individual electron migrates through the conductor. I'm going to draw a conductor here, and I'm going to draw a little electron, and then I'm going to put in an electromotive force here. And a lot of people believe that once you, I could have put a switch there to close it, but that once you apply an electromotive force across a conductor, that this little whole electron is going to travel in a straight line through the circuit from one point to the other at the speed of light. This electron might travel, 1 meter in an hour. Are you shocked? All right. Again, electric current is not defined as the flow of electrons through a conductor. That's why you're here. Let's talk about it. But first, I want to do a little demo. Okay. What you're looking at is just a piece of wood. It's a door jamb of my house. This right here I'll talk about later. That's a piece of parchment paper. That's an insulator. I've got 2 pieces of Scotch tape. I just peeled it off of a roll in my office. All right. What I'm going to do, I want to stick these pieces of tape onto the wood. quickly peel them off. Watch what happens. They don't like each other, do they? They're not happy with each other. That's called static electricity. Now, let me take those same two pieces of tape, and this time I'm going to put one of them on top of the other. Just like that. Okay, one on top of the other. I don't want them totally stuck together, so I can peel them off. Now they love each other. Now they're attracted. Okay, now that they're attracted to each other, I'm going to take one of them, put it on this side of the parchment paper. I'll stick it really good. Going to take the other one and put it right on top of that one on this side, on the opposite side of the parchment paper. And I could, if I wanted to, roll it up really tight. Really tight. This is a really bad roll, but let's say I rolled it up really tight. I've just created a capacitor. I'm storing electric charge. One plate is charged negatively, the other plate is charged positively. Static electricity. Hey, Stereo Police. One of the things I wanted to do before we get going here at the onset, or outset, or onset, I don't know which to use, of these lectures is I wanted to briefly give you my credentials with a caveat. I'm Stereo Police, that's my username. I prefer to remain anonymous, so I'm going to be rather nebulous here. I do have a full-time professional career, and I do wish to remain anonymous. I do not represent my employer in any capacity, though you should not know who my employer is, and I appreciate that. I have a background. I've got degrees in electrical engineering. Spent about 5 years as a real engineer. Actually designed a couple of things, and we produced production level drawings, made things. Since then I migrated over to intellectual property law, have an outstanding 30-year career in that, and I teach patent law actually quite a bit, quite often, so I do teach. I really enjoy teaching. Now, let me say this, for those of you who appreciate credentials. I don't care about paper credentials, and I don't really care about college degrees. They don't impress me. And I'm not saying this to impress you. I'm just telling you I do have a background in this stuff. Some of the most intelligent people I've ever met have never stepped foot into a university. The most impressive people I've ever met in my life never have stepped foot into a university. And some of the biggest morons I've ever met have PhDs, if that means anything to you. College doesn't mean a thing to me, especially nowadays. Especially now. Back in the day, it meant a little more, but nowadays I really question what college produces. Now, when it comes to the sciences and engineering, I think colleges are still solid, rock solid. When it comes to other aspects, forget about it. I think, there once was a time that universities, their goal was to teach you how to think, not what to think. They gave you the tools to figure out how to think, and then it was up to you to determine what to think. And today, universities are just indoctrination departments to help you to determine what to think. There's a vast difference. It's really, really sad. So I'm just telling you this because I do have a background in this stuff and I do have a firm understanding of it, but I'm not telling this to impress you. It doesn't impress me. There are a lot of skilled designers out there, skilled technicians. Some of the smartest people I know are actually automobile mechanics. Just intellects. Some of the smartest people I know are in blue collar jobs. And you get the point. So it means nothing to me. I just wanted to establish that for your edification. So moving forward here, what we have coming up is Audiophile University, the physics of sound for the non-technical audiophile. My goal over the next year, probably, it's going to take me a while to do this because this is not easy to do. It's time consuming. Is to present a series of lectures. I'm going to call them lectures. Try to inject a little fun and common sense into it, but to give you the fundamentals of what you need to know to teach you how to think, not what to think, about high-end audio. How to interpret reviews, how to interpret specifications, and on and on and on. I will never tell you what to think. I'll tell you my opinion sometimes, but opinions can be wrong. You don't believe me? They can be. Preferences can't be wrong, but opinions can be wrong. Just as a matter of philosophy. And I'll give you an example. I like to philosophize sometimes. I can give a person an apple and ask them, what color is it? And they'll say, I'm of the opinion this thing is orange. They're wrong. Their opinion is wrong. You see? Whereas, if I give a person an apple and an orange and say, which one do you prefer? And the person says, I prefer the orange. That can't be wrong. It's a preference. All right? So, I may give you a preference from time to time, maybe even an opinion, but I'm going to teach you how to think and give you the fundamentals of electronics as best I can for the non-technical audiophile. Moving forward, I'm going to do my best. So I just wanted to establish that. I'll never say this again. It's at the very first lecture. So let's move right along. Okay, moving right along. Let's dig into it. All right. Electric charge. Now, first of all, I want to say that electric charge, and I'm going to be going off script quite a bit. Most of these bullet points are here to remind me of what to tell you, so you're going to have to listen as well. I'm not going to read these things to you directly. But electric charge is a fundamental property of matter. And it's really ill understood in physics because it gets down into the quantum level, quantum mechanics. And there's a lot of things that are not understood at that level. But it is a property that can be measured, and on a macro level, It's well understood how it behaves, how electric charge behaves. And it's all around us. We use it. It's just the absolute basis of electronics. And that's why it's so important to start at this fundamental level. But where it derives from, where it comes from, that's like asking where gravity derives from or where that comes from. Electric charge, I'm going to go off script right here. I'm going to come back to it. And we're going to get to this later, but electric charge, well, I'll tell you what, I'll get to that in a minute. Electric charge can be either positive or negative. And you've probably heard these terms you've probably heard these terms throughout your life. Now, these terms are absolutely arbitrary. I believe, that don't quote me on this, it's been a long time, I believe they were these derived from Benjamin Franklin, I think, but don't quote me on that. Go find out yourself. But it really doesn't matter. The terms positive and negative are arbitrary. You could say they're green and blue. You could say one of them is Ralph and the other one's Joanne. The terms positive and negative don't really describe a characteristic of the charge, but it does help. It does sort of help you to remember something. Like in relationships, we say opposites attract. And you can always remember that when it comes to electric charge. Okay? Now, because in electric charge, opposite charges attract. Same charges repel. That's like, for example, if I were to meet someone just like me, I probably wouldn't like them. Seriously. Like, two strong personalities often clash. So you can think of it that way as well. Now, and I probably wouldn't like me for a lot of other reasons too. Actually, I don't like me sometimes. All right. But there are different words and they denote different characteristics. Opposite charges attract each other. Same charges repel. Okay, the unit of an electric charge, and you don't need to know this really, but it's the coulomb. We're going to get to that later. And there's an elementary charge we denote as E. Because when we dig down to the smallest forms of matter, things are quantized. Things are more digital than they are analog. It's really weird. And there is a kind of a smallest unit of charge. It's called the elementary charge. And it's denoted as E. All right, so the electron bears a charge of negative E, and a proton in an atom, we'll get to that in a minute, bears a charge of positive E. All right, so I'm going to draw a little E here, positive for a proton, a little E here, a negative for an electron. And now here's what I wanted to get to earlier. Now, they are attracted to each other because they're opposite charges. But there is a distance between them. This is really interesting. So, they're attracted to each other by virtue of a force. Now, there are a couple of different kinds of forces. And I want you to think of one kind of force as a direct force. Now, if I were to come up to you and push you in the chest, I don't mean in a violent way, I mean in a demonstrative way, push you in the chest and you were to sort of drop back by 1 foot. I applied a direct force to you, and that caused a reaction, a repulsive reaction. Or if I grabbed you by the shirt and pulled you towards me, that would be an attractive force, but that's a direct force. I applied direct force to you. Whereas an electrostatic force that exists for example, between this here proton and electron, each of which has an elementary charge, this kind of force is referred to as a field force. It's not a direct force. It's a force that exists within a field. And you can kind of see this field being demonstrated right here by virtue of field lines. There are a couple of kinds of field forces out there, and I want you to think of a magnetic force. Same kind of thing. Remember, opposite poles attract, same poles repel, sunny side of the magnet. There's another kind of field force out there called gravity. And I'm going to draw two different guys. This guy's a real skinny guy, and this guy is rotund. All right. Oh boy, he's not a real looker, is he? Now, which guy weighs more? Well, force equals mass times acceleration. We're talking about gravity now. All right. So this guy, each guy has a mass. This guy is way more massive than the skinny guy. So his force being force times mass times acceleration. Now acceleration is the acceleration of gravity. That's a constant. The only thing variable here is the mass between these two guys. So the more massive guy is going to have a higher force exerted on him by gravity. Okay? That force right there is his weight. So when you're weighing yourself, you're just basically determining the force exerted on you by gravity. Gravity is a field force. It's not a direct force. Interesting, huh? Now, let's get back to the lecture. I digress. Moving right along. Now, that's a good segue, as I just mentioned. An electrostatic force is what we call it, is expressed in units of newtons. Now let me go back here. When we often weigh ourselves, we weigh ourselves usually in the US in units of pounds. Okay, but most science is done in metric. All right, so the electrostatic force is expressed in units of newtons. Okay, and that's just a measure of force, across physics. And so what we have, and there's an equation for it. We're not gonna. It's beyond the scope to dig into these equations. But the one thing that is what I want you to take away here is this: there's a distance. There's a distance between two particles. So you have two particles here. Now I want you to note that this particle is negatively charged and that particle there is negatively charged. And let's just say they're both electrons. So they're the fundamental particles. And they each carry a negative charge. And they're separated by a distance, r. So the force, and of course they're negatively charged, so what are they going to do? They're going to repel each other. That's why these arrows are facing in opposite directions. They're going to repel each other. And they're repelling each other because there's a force pushing them away, the electrostatic force. And that force is going to be proportional to the square of the distance between them because it's a field force. All right? But forget the square part of it. We don't need to get into that. The point being is the further away these particles get, the less force they experience between them because it's a field force. The force diminishes the further they get away from each other. The same exists over here, except let's say we have an electron and we have a proton, and they have opposite charges. That means they're going to attract each other. That's why the arrows are facing in. Same thing. The closer they get, the larger the force is going to be. The further apart, the less the attractive force is going to be. And this kind of forms the basis of a capacitor. We'll get to that later. But that's the point. There is a force a field force between charged particles that causes either attraction or repulsion. And that force is also proportional to the distance between them. Okay, moving right along to atoms. If you kind of remember your high school physics, an atom has protons, neutrons, and electrons generally, with some exceptions. And okay, the protons and the neutrons are clumped up into the core in the center of the atom. And they're all hanging out together. Remember, the protons are positively charged. Now, the electrons are orbiting. I don't like to use the word orbit. They're orbiting, though, in these bands. I'm going to use plain language here. And they're often depicted like planets orbiting a sun or something. And that's not exactly what's going on the quantum level. In reality, and I'm digressing, I'm going to get back to this. In reality, these electrons don't really exist. They only exist when necessary. They're kind of there and they're kind of not there. It's really weird, man. But they are there at a certain distance. And they exist in a certain space. But they're not really actual particles that are moving around like planets. There are possibilities of locations for this thing to exist when it needs to. Now that's way too deep. Let's get back to what we're talking about here. But for the purposes of this overview, you can just imagine an electron as a little particle, like the planetary model here, okay? Just imagine it. And they exist certain distances from the center. Now, again, protons have positive charge, electrons have negative charge. Neutrons have no charge. That's these green things here. Okay? And I say center, it's called the nucleus, okay? I'm trying to use plain language, but you have the slides to read here. All right. And again, this is tedious, but we're getting somewhere with this. I'm never going to go this deep again. Proton has a charge of a positive 1.602 times 10 to the negative 19. Ah, what a small number, right? An electron has the same charge, but of opposite polarity. It's negative. So they're the same charge. The neutron in an atom, we don't need to worry about neutrons. They don't have any charge at all. They're neutral. And of note, look at the size comparisons by virtue of mass. Electron is very, very tiny. Much tinier than that. We had to draw something there. Compared to the relative sizes of protons and neutrons. Okay, but these are the quantized elementary charges right here. They don't change. That's what an electron has. That's what a proton has. It ain't going to change. These are charges in coulombs. All right, so the important thing is that, and we're mostly going to talk about electrons from here on out because that's what carries the charge. It's a charge carrier. And when we talk about current, remember I said that current is not the flow of electrons? This is really important. We're going to talk about this later. Current is not the flow of electrons. Current is the flow of charge. Electrons are just the taxi cabs that carry the charge. Right on? We're going to talk more about that later. All right. Again, Being repetitive because it's important. Opposite charges attract. So we have a proton, we have an electron they're attracting. Now, if you had two protons near each other of same charges, they're going to repel. If you had two electrons near each other of same charge, they're going to repel. And again, the amount of force acting on the two charges depends on how far away, I can't draw, how far away from each other they are. Okay, this is electrostatic force. Now let's look, I'm skipping a whole lot of stuff here. Let's go to an insulator. Now there are, in electronics, we have the concept of insulators, the concept of conductors, and the concept of semiconductors. We're not going to talk about semiconductors today. I'll hint at it at the very end. Let's start out with what an insulator is. You think of insulators all around us, like wood, glass, plastic. They really don't like current flowing through them. They insulate. Rubber. Okay. And an example is a carbon atom. You know, and I'm showing you a carbon atom right here. Now a carbon atom has 6 protons and 6 neutrons and 6 electrons. And these electrons, there's only 2 shells right here, or 2 orbits right here. And they're kind of really close to home. They're kind of, remember, distance matters in terms of force. They're all kind of close to home. They're kind of close to their protons, and they're very attracted. Very, very attracted. So to free one of these electrons, to bounce them off, to move on, to create an electric current, to carry that charge, really, really hard to do. Maybe a bolt of lightning might do it. It would take a lot of electromotive force. This is an insulator. Let's go to copper. We all know, most of us know that copper is a damn good conductor. It's not the best conductor, but it's cheap, and it's all over the damn place. So, copper is a good conductor. Now, as we can see here, copper has 29 protons and 29 electrons. I don't care about the neutrons. And look out here, 1, 2, 3, out here in the 4th orbit, I'm using plain language, there's this little old lonesome electron. This orbit is not filled like these are. See, once these orbits get filled to their capacity, then a new orbit starts up and it allows it to get filled. Well, there's one little lonesome electron out here. This is what makes copper pretty special. This is what makes all conductors special. There's one little electron, a charge carrier, and he's all by himself out here, and he's way far away, exponentially further away from the protons. So remember, the force of attraction is far less because of the distance differential. So he's loosely bound out there. It's much more easier to kick him right off and have him move on. This is a conductor. Okay, and by the way, I forgot to mention, for every slide, you'll see the source I took it from. I'm not plagiarizing here. I'm using this for educational purposes. And you're welcome to visit all of these sources. I encourage you to visit these sources if you like something. So what is copper? Copper is a kind of atom that only has one electron in its outermost ring. I call them orbits, call them rings, bands. Okay. So there he is. This guy is really important. All right. It's called a valence electron, technically. Now remember, electrons are charge carriers. That's something you have to commit to yourself. Electron is a charge carrier. It carries a fundamental charge of 1 point blah 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 10 to the negative 19 coulombs. It carries a negative charge. Now if we can free this electron from the atom and force it to move, we can create an electric current. You see? That's how it's done. Now here's a nice little depiction. This is actually, if you go to this website, this is an animated depiction. And what you'll see is, now I'm gonna modify this right here. I'm gonna say, let's just say this is a wire. And you know, if this is a wire by itself, these for the most part, and these are the valence electrons right here. These are this lonely guy in the outer orbit. That's what we're not going to depict the inner orbits here, okay? I'm going to draw. Now electrons move from negative to positive. So I'm going to draw a battery, an electromotive force. Okay? And you often hear, this is called electron flow. You will see depictions of current flowing from positive to negative, and that's called conventional flow. And that's the way a lot of textbooks show it, because early on in science, we got it wrong. And it just kind of stuck. But electron flow, this is actually the way electrons do flow from negative to positive. All right? So, once I apply an electromotive force, E, M, F, let's say it's a battery. Now I'm applying a force. And that force, if that force is enough, I can kick this electron off and he's going to get freed and he's going to roam around and kick this guy off and take his place. He's going to roam around, and this is actually depicting a free electron right here, you know, and so on and so forth. Let me see if I can give you a depiction of this. Hang on just a second, of this animation. It's better than the way I'm describing it, because I'm a knucklehead. All right, here you go. That is not exactly a great depiction of what happens when current flows. Not exactly, and I'll explain later, but you're seeing valence electrons leave their orbits and enter an orbit of another atom. And you're seeing the general flow from left to right, caused by an electromotive force or voltage applied to a conductor. All right. Okay, so conductivity. Some atoms are better than others at releasing their electrons. We just talked about that. The ones with valence electrons that have orbits way out there. Elements with high conductivity are that have a lot of mobile electrons are called conductors. And examples are like copper, silver, and gold. Elements with low conductivity, such as the carbon atom I showed you, are called insulators. And examples are glass, rubber, plastic, air, many others. Even water in its pure state is a good insulator. Wood. All right. Now, I mentioned a while back that current in a circuit is not the flow of electrons, it is the flow of charge by definition. Electrons are just charge carriers. You know, like I said, they're the taxi cabs that carry charge. So the definition of current, it's simply the quantity of charge, and Q is charge in coulombs, that passes cross-section of a wire in a given time. So if I had a wire, I'm going to try to draw all this, okay, and I took a cross-section of it, and a cross-section is, I'm going to look at it from this direction right here. It'll be a circle, right? So whatever, actually let me not look at it that way. Let me just take this cross section and then let's view it like this, even though it's infinitesimally small. It's just a cross section. Okay? Now, it's the amount of charge that passes this threshold in a given period of time. Okay, so electrons are charge carriers, so technically it is the amount of electrons that passes that threshold in a period of time, but it's not defined that way. It's the amount of charge, see? Current is Q divided by T, the amount of charge passing over a given period of time. The electrons are just charge carriers, but electrons don't just travel in a straight line. And this is where it gets weird. And this is why I say a current is not the flow necessarily of electrons. It's the flow of charge. I'm going to explain that. All right. Now the ampere, and this is a unit that we see all the time in audio. Amps, amps, amps. The ampere, or the amp, is just an abbreviation. Is a unit denoted by A. 5 amps. Right on. Actually, that's a lot of current. Okay? So a current of 1 ampere means that 1 coulomb of charge passes through a cross section of wire every 1 second. I equals Q over T. Okay? 1 coulomb, 1 second equals 1 amp. Make sense? This is how current is defined. Electrons are only involved because they carry charge. But it's the charge itself that's the current. Okay? So let me say this. Coulombs. What's a coulomb? Okay, if the electrons are the taxicabs that carry the charge, okay, and 1 coulomb of charge over 1 second equals 1 amp, then how many taxicabs do I need to pass through a cross-section of wire in 1 second? Equal 1 amp. This many. Okay, look, I don't even know what this number is. You guys tell me. If this is 100 and this is 1,000, I'm sorry, and this is 1,000, 10,000, 100,000, 1 million, 10 million, 100 million, 1 billion, 10 billion, 100 billion, 1 trillion, 10 trillion, 100 trillion. What comes after that? A gazillion? 10 gazillion? I forget. This is a lot of electrons, folks. This is a lot of electrons. But I don't want you to think, I'm going to keep re-emphasizing, I don't want you to think of current as electron flow. I want you to think it as charge flow, and I'm getting to that. I'm going to tell you why. There's a darn good reason for it. It's right here. And I almost want you to stop and don't listen to me and read this if you can before you listen to me. But I'm going to go forward with it. Current has to do with the number of coulombs of charge that passes a point in a circuit per unit of time. Okay, it's often confused with drift speed. Now, drift speed refers to the average distance traveled by a charge carrier, such as an electron, per unit of time. And this is when people say current is the flow of electrons per, that's what it is. It's not. If you want to talk about the flow of electrons, we have to talk about drift speed. if you want to talk about current, we have to talk about the flow of charge. Now, this is where it gets surprising. The drift speed of an electron moving through a wire is like a distance to time ratio. Now, here's the key. I'm not going to get too technical, but here's the kicker. The path of that a typical electron takes is chaotic and zigzag, like this right here. So if I were to apply an electromotive force and start kicking those valence electrons off, and if I was able to follow an electron, which you can't, but if you were able to, and the path that this electron would take moving forward would be chaotic and zigzag. You see this? It even goes backwards. So, here's my electron. I apply it this way, that way, that way. Oh, go backwards. Okay. But generally, it's making progress forward. But it's not traveling at the speed of light. Okay? That one electron, in fact, the typical drift speed might be 1 meter per hour. That's slow. So you can't think of electrons as just traveling in a straight line through a wire at or near the speed of light, and that's what current is. If you want to think of electrons, here's a second electron, right? Here's a third electron. Man, it's a chaotic mess. But they're all generally moving forward based on the electromotive force applied. So, I don't want you to ever think about drift speed ever again. I'm just giving you we don't need to worry about that. We don't need to concern ourselves. We need to concern ourselves with current. And I'm just giving you the basis of it as the flow of charge. Now, so if the electrons are so doggone slow, how can you have a high current? How can you have a high current? Well, a high current means a lot of coulombs of charge passing through a cross section at a given time. Well, here's the kicker. If I've got tons of these electrons and I got a ton of them all at the same time, all over the place. And they may all be moving randomly and chaotically, but there's a ton of them waiting at the threshold. And remember, they're all making general progress forward. If there's a ton of them at the threshold, even though they're moving slowly, but there's a ton at the threshold. And as soon as you open that door, it's like the door at Walmart on Black Friday or whatever. They all are walking in kind of slow, but there's a ton of them because they're all pushing up against you. There's a ton of them, and each of these electrons is a charge carrier. And that's how you can get a high current, even though they're moving slowly. That's how you get a high current. Because it's the flow of charge that's passing through. There's a ton of these guys at the threshold. They have a little analogy here. Is this the analogy? Let's see if there's an analogy here. Okay. So here's an analogy. I'm going to read this to you. Suppose there's a very large turtle race with millions and millions of turtles on a very wide racetrack, okay? So millions and millions and millions and millions and millions of turtles, okay? They're all turtle, 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 turtle. That's what I'm drawing. It's just millions and millions and millions. And then here's the finish line. Now, each of these turtles is slow as a turtle, right? It's slow. They don't move fast. They have a very slow drift speed. Now, at the start of the race is
1 meter in length. 1 meter. 1 meter in length. Okay. 30 minutes after the start of the race. Okay. A large percentage of the turtles reach the finish line at the same time 30 minutes after the race. In such a case, the current would be very large, with millions of turtles passing the point in a short amount of time. Because there's so many of them. There's so many of them built up here, even though they're all moving very slow, but there's just millions of them passing the finish line at the same amount of time. Because they're small relative to the width of the racetrack. But their drift speed is low. And each turtle is a charge carrier. So speed has nothing to do with it. Okay, the current has to do with how many, this is it, the current has to do with how many turtles cross the finish line in a certain amount of time, not their speed. Same with electrons. All right? I'm not going to read this to you, it's too technical. We're almost done here. Now, I mentioned that electrons are charge carriers. And they are. They're the taxi cabs that carry the charge. However, there are other types of charge carriers in electronics, and they include holes as well. Electrons and holes, especially positive holes. And typically these exist in semiconductors. And I'm not going to get into that now, and this is just an added bonus here for you, but in semiconductors and other materials, and this is a depiction of a lattice of atoms. And you see how we have a silicon right here, I think is it silicon. And then you can dope the silicon with another type of atom, and that other type of atom leaves a vacant space. So remember, with copper, we had this valence electron, this extra electron out there hanging out, waiting to be popped off. But in this matrix of atoms, because of this doping, we have a vacant space. Instead of having an extra electron, we have a vacant space called a hole. And that hole is ready to be filled by other electrons in motion. And we have something called hole current. And that hole is considered to have a positive charge, equal in magnitude to the negative charge that the electron had. And a hole is the absence of an electron in an atom. And I'm going to leave it at that. So there are other types of charge carriers. Holes are the most common you would find in electronics and mostly in semiconductors. All right, there we have it. End of lecture 1. I hope that wasn't too confusing, but the big takeaway is charge is the foundation of everything. It's a fundamental nature of matter. And from here forward, always think of current. Always remember that when you have two charged particles, they can either attract or repel. And the force exerted on these particles, if they're attractive force or repulsive force, depends on the distance between them. And an electron is a charge carrier. It carries a fundamental charge in coulombs. And when a current, this is a wire, when an electromotive force such as voltage is applied, okay, I'm going to draw some electrons in here, is applied to a conductor such as a wire, that these electrons do not move in a straight line. They move in a chaotic path, and their speed is called the drift speed, and it's very, very slow. But the current we measure is not based on the speed of these electrons. It's based on the number of these electrons that pass a cross section of that wire in a given period of time, and each electron is a charge carrier. That's what current is. All right? Oh, wow. Didn't think I was going to get through that. So that's the end of lecture 1. If you have any confusion, you can follow up on some of these websites. I think I'm going to try to post this in the cloud for you guys. But again, you can pause and stop and check out any of these sources. I've given you a source for everything I've taken from. And I'm glad I did this. I was going to come up with my own slides, but it's a time saver for me, and some of these graphics are way better than what I could come up with. All right, Stereo Police. End of lecture 1. This is the foundation for everything. Thank you for joining me. I hope this was helpful. I do it for you. I do it for nothing. Ciao.